Welcome to part 2 of vector representations. So we continue with the example in which we're considering a specific vector of C4 here with entries 6, 14, 6, and 7. And we want to represent this vector relative to different bases. Okay, so one thing to continue to remind ourselves that even though the vector y stays the same, since we're considering different bases, different sets that are linearly independent and spanning, then the so-called representations are going to be changing. Relative to these bases of C4 with these specific column vectors, we found that the vector representation called rho here has entries 2, -1, -3, and 4. But now we're going to consider another basis of C4. Okay, and so this is another set of vectors, and this is a set C such that the span of C is exactly equal to C4. So writing Y as a linear combination of these vectors is going to again lead to a situation in which um, we're solving a linear system, and the scalars that we're interested, the scalars are going to be precisely what determine the vector representation. Those are the variables in that linear system, and we can form a matrix with these 4 columns. We can define a matrix that contains these column vectors as its columns and use that in the calculation of solution set. So this is no other thing that asking a question is why a member of the span of this set C. And the process of asking that question, which leads to calculation of solution set, then we find that there are scalars, okay, -28, -8, 11, and 0, for which this linear combination with those scalars exactly equals the vector y. And therefore, we collect the scalars. We would collect the scalars 28, -8, 11, and 0. They're collected into this column vector, which is what we call the vector representation of y relative now to a different set, different set that is linearly independent and spanning. That set is here called set C. So relative to that basis C, we have a representation that involves -28, -8, 11, and 0. So let's talk now about the standard unit basis. Remember this E1 is a vector with 1, 0, 0. These are the columns of the 4x4 identity matrix. E2 would be 0, 1, 0, 0, right? E sub 3 would be 0, 0, 1, 0. And finally, last but not least, we would have 0, 0, 0, 1. Okay, so here, this is E1, this is E2, this would be E3, and this one would be E sub 4. This is a standard unit, the basis with the standard unit vectors, and we could represent, if I go back, look at, say, for example, what happens if you multiply 6 times E1. Well, 6 times E1 is 6 times 1, 0, 0, 0, and this multiplication becomes 6, 0, 0, 0, right? So if we add 6 times E1, okay, 6 times E1 to 14 times E2, this vector here in the middle is going to be a vector that has 0, 14, 0, 0, okay? And we add that to another vector that looks like 0, 0, 6, 0, and that also is added to a vector that looks like 0, 0, 0, 7, okay? So by adding these 3 vectors, this linear combination is exactly equal to the vectors stored in 6, 14, 6, and 7. So this is a convenient way of a representation, the representation with the basis that contains the standard unit vectors, in which is almost by inspection. You could still do what we were doing in terms of calculation of solution set, but here you can also see this directly by inspection. So the representation, the vector representation relative to D, okay, in this case, that vector representation relative to D is this row operator, which has entries 6, 14, 6, and 7, the exact same entries of the vector, but it doesn't matter. That is the vector representation relative to the basis D. So one thing to note is that order in which the members of the basis, the order in which the basis members are listed, that order matters, okay? So consider now a set that contains the same elements as the set D, and these are the standard unit vectors, but they are now listed in a different order, okay? So order matters here. So with this listing where E3 is first, right? So this is basically like a permutation of the columns of the identity matrix. So the first vector here looks like 0, 0, 1, 0. Okay, that would be the first vector. And the second vector would be 0, 0, 0, 1. So here is E3 and this would be E4. And the other vectors we know, right? So the vectors, this is 1, 0, 0, 0, and this one C would be 0, 1, 0, 0, right? So this is E2 and this is E1. Now they appear here listed in a different order, which means that when we write down the linear combination, okay, we write down the linear combination relative to E, we're multiplying now by each of those vectors. So we have to multiply 6 times E3, 7 times E4, and so on, right? And so now we have a vector representation relative to E that reads 6, 7, 14, and 6, and this is not identical to the original vector as it was when we were looking at the basis D. So for every possible basis of C4, we could construct a different representation of Y.